Hi everyone, this is Jake Fry, and today is going to be my second video for Intro Mechanics. This time I'll be talking about scalars and vectors. Once again, this will be mostly mathematics, but we're getting much closer to actually talking about physics, which is great. Alright, so first, what's a scalar? So, in fact, there are many different physical quantities that are only described with a magnitude or size and a unit. So these include things such as time with seconds or minutes or hours, temperature with Kelvin, Fahrenheit, Celsius, speed, or mass with kilograms. So the key part about scalars is that they don't have a direction component implied. So we do not do things like ask if the time is different downstairs or upstairs in a house. We just ask, oh, what's the time? Yeah. So if we care about what direction a quantity has, then we use vectors instead. These include things such as position, velocity, acceleration, and force. So I know previously I said speed, and so you might think, oh, what is different between speed and velocity? Well, in fact, speed doesn't have necessarily a direction included, so velocity does. So if I were to say, like, oh, the car is traveling, 60 miles per hour, that's speed. But if I were to say the car is traveling 60 miles per hour north, well, that has both a magnitude, 60 miles per hour, and a direction, north. So that would be a velocity instead. So just be careful. It has both a quantity that is a magnitude and a direction. All right, and as I guess previously said, the length or the size of a vector is in fact a scalar quantity known as the magnitude. Okay. So you might think that vectors and scalars are completely different things, but you can actually generate vectors of interest by doing things like finding the rate of change of a scalar quantity across a house, like in this example. So if I wanted to find the rate of change in temperature as I move further away from a fireplace, then I could create a temperature gradient, and that is actually a vector, even though each temperature measurement that I take is just a scalar. So doing things like taking gradients of scalars, I'll get to much later in the lecture series, but just, to keep it in mind. All right, so now I'll go on to what's the best way to perform simple operations on a vector. So, many textbooks discuss visually adding or subtracting vectors by drawing them. But this actually comes with a very big problem. So if you're really bad at math, or you don't have graphing paper, and you can't, draw perfectly straight lines, or you don't want to do an infinite amount of trigonometry, this is not the best way to do it, because you can very easily mess up if you're not a good artist. So in fact, the best way is to decompose the vector into separate components based upon a conveniently applied coordinate system. This way, there will be no ambiguity on any of the operations you perform on any vector that you have. So, how do you decompose a vector? So, first what you do is you apply a convenient coordinate system. And you can choose the coordinate system to be whatever you want, so long as it's convenient for the problem that you want to be solving. And so, just if you want, a brief introduction to coordinate systems, you can watch my previous video. All right, so each vector component actually consists of a scalar that gives the magnitude of the vector along that specific coordinate direction. So if we have this vector A, call it A, where I guess here you see my notation, I say that a vector is using boldface font. Other people might have, a vector shown as just an A with like a right facing arrow above it. Sorry, I forgot what I was going to say. But in this case, I'll always have boldface font. And scalars will always be either italicized or just not boldface. Okay, so we can decompose this vector A into our coordinate system. So in this case, I'm using a generic three-dimensional coordinate system. So in the first box of this row vector is the scalar A1, the second is the scalar A2, and the third is the scalar A3. And so each one of these boxes in this vector are different coordinate directions. That's what it's implied when you have a row vector such as this. Another way that you can write it is by saying, okay, A, the vector, is the sum of a vector A1 plus a vector A2 plus a vector A3, which is true. Each of these coordinate directions have a magnitude, and so you can add them together. And this can be shown to be equivalent to A1 times the unit vector along the direction of the first box plus A2 times the unit vector along the second box plus A3 times the third vector on the third box, where, let's see, the unit vectors E1, E2, and E3 are defined as such. So these are three separate ways to decompose the same vector using the same coordinate system. And I'll, say which one I like more later on. Okay, so now how do you decompose this if you were to use 3D Cartesian coordinates? So instead of using A1, A2, and A3 for the three different coordinate directions, we can use AX plus AY plus AZ, where you can see each of these vectors along each coordinate direction. AX is this gray one, AY is this one, and AZ is this one. And if you sum them all together, if you drew them, like I said, is more difficult, you can see that the sum of this vector, and this vector gives you the black A vector that we're decomposing in the first place. Now, convention has it that the unit vectors along the x direction is given by I, the y direction is given by j, and the z direction is given by k. So we can also decompose it being ax times I plus ay times j plus az times k. Okay, so now addition and subtraction. So by decomposing vectors into coordinate systems, we have a very convenient feature that you can just add up the scalars that multiply the unit vectors out front. So if I wanted to do a plus b, then I would just look at, okay, what's the component along the first coordinate direction, E1. Well, for A, it's A1, and B, it's B1. Those are scalar components. And adding scalars, there's no direction that you have to worry about, and so you can just add them up and multiply by the unit vector E1. Similarly with A2 plus B2 and multiplying E2, and A3 plus B3 multiplying E3. And so this, you don't have to worry about, how good your drawing is. All you're doing is adding up scalar components, and you get directly what you want, A plus B. Okay, also, multiplication by a scalar is very easy too. So you can multiply by a scalar quantity r, and it just multiplies the scalar component for each coordinate direction. And so instead of trying to, if you have a vector this long, you're saying r is 2, trying to, draw perfectly twice the length, you can just do it much easier by multiplying the scalar components. Okay. Now, how do you find the magnitude of a vector? This is important in many, many different parts of physics that we'll get to later. And it is simply, all you do in, 3D is take the square root of the squared components, all added together, all the squared scalar components added together. And if you have a lot of linear algebra experience, you'll notice that this looks very similar and is actually identical to the square root of the dot product of A with itself, which we'll get to later, what dot product means. Okay, and so then you can generate unit vectors on your own with whatever direction you want. So like the unit vector along A, unit or unity just means 1. So what you do is you just take the vector A and you divide it by the magnitude that you calculated. And so you can see it spread out in component form, that you just divide each scalar component by the magnitude. And if you were to go back and plug this into the square root of the dot product, you would find that the magnitude of A hat is just 1. Okay, so now going on to what I find most convenient. So I believe that the most convenient way to write a vector is in column vector form. And so this is because it is directly analogous to vectors in linear algebra, and so you get a lot of useful tools such as matrix multiplication that you can use. And so formulating physics using linear algebra is always going to be the best way in order to understand physics. So just get used to it now, I guess is what I'm trying to say. So, for example, position vector x can be written with each of its components in this vertical or column vector format, where each coordinate axis is described with this subscript 1 through n dimensions. And say you wanted to see what happens if you transformed this vector, so you could rotate it, you could stretch it, you could do whatever you want to it with this operator A, given by this matrix, where each element has a separate number. So yeah. And so you can do matrix with vector multiplication. So it'd just be, when you multiply these together, you get your resultant column vector y, which is just the first component of vector A, matrix A with the first component of x, all the way up to xn on the first row. So the first row, if you remember, so a1, 1, all the way up to a1n, and so on with the second row all the way up to the mth row. And so this makes it so that by writing your vector in column vector format, you get all this matrix multiplication rules, very obvious. And also, if you're more used to computer science, lots of things like arrays in Python or NumPy or in MATLAB, you get all of those useful tools at your disposal as well. So yeah, much better than just drawing the arrows and seeing what happens when you add them together. Okay, so now we can get into more complicated decompositions of vectors. And so I showed before with Cartesian coordinates, so along x and y, where you have unit vectors e1 and e2, you can decompose this blue vector v in such a way: x, the scalar x quantity multiplied by e1, plus the scalar quantity y multiplied by e2. But you don't have to use a orthogonal coordinate system, and you also don't have to use a coordinate system with a grid spacing equal to unity. So you could use this, rather crazy looking coordinate system where one direction is along f1 and the other is along f2. But you'll notice that if you were to sum them together, so f1 plus f2, you would get v. So you can use rather crazy looking coordinate systems and get a different decomposition of the same vector. Okay, so now what are some more normal decompositions that we might use? So, of course, polar coordinates is the next step, as you would see from my previous slides on coordinate systems. But I'll just jump straight to cylindrical coordinates. So remember, you have your rho vector, which is the radius. You have phi, which goes from 0 to 2 pi, so it goes all the way around the, I guess, with the z direction as its center of axis. And you have z, which is just in the z direction. And so we can see how two different decompositions of vectors might look like. So if you had things written in Cartesian coordinates, we know that rho is just the hypotenuse of x and y. So it's given like this. The phi, you can see just by trigonometry, would just be the arctangent of your y component over your x component. And then, of course, because it's cylindrical coordinates, your third axis z is the same in both cylindrical or Cartesian coordinates. You can also go the other way. Say if you have a vector written in cylindrical coordinates, you can transfer it to a vector in Cartesian coordinates just by using, once again, trigonometry. To find x is the same thing as rho cosine phi, y is the same as rho sine phi, and z is still z. Okay, and then it's useful to know what the, I guess, the unit vectors are for given coordinate systems. And so we can use the matrix multiplication idea that I previously discussed to see that the transformation of the unit vectors in Cartesian coordinates to those in cylindrical coordinates is given by this. So just to refresh you how you get rho hat, it would just be multiplying cosine phi times x hat plus sine phi times y hat, and so on. Okay, so now slightly more complicated, but still very useful, how to decompose a vector into spherical coordinates. So in this case, again, the first coordinate is just the radius, which is given by the hypotenuse, this time of 3 different coordinate directions when you're converting from Cartesian coordinates to spherical coordinates. Theta, in this case, it looks very crazy, but remember theta in physics, at least, it goes from off of the z-axis from 0 down to pi, down here. And so you can generate theta by arc cosine of z over the hypotenuse. And phi, again using more trigonometry, is just given by arctangent of y over x, and it spans from 0 to 2 pi. So it might be a little bit weird in all these cases having angles that don't span from negative infinity to infinity, but that's just how it goes with spherical or cylindrical coordinates. And so then if you wanted to convert from spherical coordinates to Cartesian, it's just given by this. So x is just r sine theta cos phi, y is r sine theta sine phi, and z is r cosine theta. Each of these is can clearly be seen from the trigonometry. All right, and so then it's a little more complicated, but similar idea for converting from the unit vectors in Cartesian coordinates to those in spherical coordinates. You have this transformation matrix. So, for example, r hat would just be sine theta cos phi times x hat plus sine theta sine phi times y hat plus z plus cos theta z hat. All right, so now that we know how to decompose vectors in multiple different coordinate systems, we know how to scale vectors by a constant, we know how to add them and transform them, we're ready for our next step in learning some physics. So thank you for listening, and don't forget to subscribe and send any comments, or if you want any examples, just send me a comment. All right, thank you.